Andy, do you see the screen share?
Yes,
I
we
get
do.
your presentation now, yeah. And then we can probably start in 1 minute. Let's just wait for more attendees to come back from the break. So let's start at 10:02 a.m. Pacific time. Yeah. Go ahead, Mike. All right, it's yours.
Okay, thank you. Well, good afternoon, good evening, good morning, everybody. A very wide audience here. So I'm going to be talking today about maintaining performance and availability after your system has encountered a short-term performance problem. My name's Michael Hallis. I work for the Real World Performance team, and I've been working with Oracle for many years. I do need to start with the safe harbor statement, even though most of the features that, or all of the features that I'm describing are going to be in the documentation. There are some of the features that are relatively new, so I'll use the safe harbor. When I was preparing this presentation, I thought, there's many possible titles here, and some of the things that we're going to be looking at is connections, processes, and sessions. Basically, how the application interacts with the database and how the application development team and the DBAs can work together to make sure that overall the system stays reliable and of a highest performance, even in the event of the types of instantaneous problems that can occur too quickly for a human being to react. So a little bit about the team Real World Performance. For those who are new to this session, we're part of the database development organization. We have team members at headquarters and elsewhere in the USA, also here in Europe and in China too. Across the team, we have 300 plus years of experience, and I'm personally about 10% of that total, which, as Mark was pointing out before, must make me one of the grey-haired people. The work that we do is basically several different aspects. We aim to use the product as it was designed by our development teams. That's sometimes easier said than done because, of course, we do have the benefit of being able to talk directly to them rather than just relying on the product documentation and so on. But essentially, we're trying to use the product the way that it's most natural to make use of it and get the best performance that we can from the product. We do that by applying data-driven analysis to the information from the database itself. So we make extensive use of the instrumentation that's provided in the database so that we can avoid guesswork. And from that, we learn lots of new information. I tend to think that I learn something new pretty much every day of my working life. So we work hard to share what we learn, not just in sessions like this, but also with our base development organization, so that we can improve the quality of our product and broaden the range of applications that it can support efficiently. So the overall theme for today is really going to try to cover some things for application development, some things for DBAs, some things for operational folks, and more. So I tried to cover quite a lot of ground in this presentation. And we're going to start with some basics of how connections work in Oracle and how managing connections can have a very big impact on not just on performance, but also on the ability to sustain performance over time. Then we're going to come back and look at what happens during a glitch, and I'm going to give you some guidelines that have worked well. They serve us well for lots and lots of different workloads. And then, because we have hopefully a little time left at the end, I'm going to look at a new feature in the product that was first introduced in Oracle Database 18c, but actually is more widely documented and more fully featured in the latest release, which is Oracle Database 19c. And this will be specifically for customers with high-end OLTP systems. And overall, the theme of this presentation is pretty much dominated by OLTP. So I'm going to start out with some real basics. Some people will know all of this and a lot more, but I always find it useful to give a little bit of a context to the more complicated situations that we're going to look into later. So getting some work done in Oracle requires me to have a database session, which is essentially a memory structure in the database. But to get that memory structure established, I need to connect to the database using some application. So for the simplest case, I'm going to just consider SQL Plus on Linux. People who are on the chat may jump in ahead and say, oh, there are lots of different variations on this, but I'm going to take the simplest case to start off with on the Linux platform. So when I start SQL Plus, I want to establish a connection between my SQL Plus process and a foreground process in the database. And it's the foreground process that essentially will access the or create the session and then use the session to manipulate tables within the database. So a session is basically a connection that has been authenticated using my credentials. So essentially that's what makes me different from other users in the database. So once I have that, away I go and I can do my work. So we have a very simple model, application process, in this case SQL Plus, connected through to the database, and we have a database session that's essentially keeping track of the memory structures, keeping track of the work that I'm doing. Now, a foreground process is in OLTP land. When I run a statement, that statement is going to be relatively short duration. So there's no point trying to run that on multiple CPUs at the same point. So essentially my foreground process can run on at most one CPU at any point in time. And in a modern system, there may be many, many CPUs available. So although this strategy of having a foreground process for me works great for me, it doesn't necessarily exploit the full power of the platform. So Oracle does rely on having multiple connections, multiple active foreground processes in order to exploit the power of multiple CPU environments. So, simple question, and as Mark pointed out earlier, we can't really do Q&A in this until towards the end, so I will ask my own questions and try my best to answer them as we go along. So, simple question would be, well, if I need multiple connections to generate the most throughput from the database or to use multiple CPUs, is it fair to say that more connections is going to be better? And the truth of it is that that is the case up to a point. Essentially, most workloads in enterprise scale systems will need multiple connections to be able to generate the throughput demanded by the application. But we don't want too many processors connected to the database because it wastes resources. And the typical resource that having lots of processors is going to waste, it's memory. So we're going to waste a lot of memory, and it will also, you know, having all those processors around doing not much doesn't make the system any more efficient. But if we have too few, as Mark showed during the previous session with his batch example, if we have too few processors, that actually can be a bottleneck in the system. So what we're aiming for is this magic number that is just right. Easier said than done. So in most modern applications, we move well beyond what SQL Plus can do with its simple client-server model, and most modern applications are built with connection pooling in place. And essentially, connection pooling is a mechanism that the application uses to try to achieve just right. So how does this work? Well, the connection pool starts with a minimum number of connections to the database. So in this case, just for simplicity, I've drawn 4 connections through to the database. That will be able to support a certain level of workload. The application will operate by borrowing a connection from the connection pool, doing some work, and then returning it to the connection pool. So in principle, even just a few processes as we have here, a few connections rather as we have here, can support quite a high level of workload, especially in an OLTP environment, because we're borrowing from the connection pool, doing our work, which might just take a millisecond or two, as in the previous examples that Mark showed, and then we hand it back again. But if the demand increases far enough, then the idea with the connection pool is that the connection pool will wait until somebody, some application session requires a connection and there isn't one available because they're all busy doing something for somebody else. And at that point, it will create more sessions. So essentially expanding the number of connections to support the workload. If the workload decreases, say if everybody goes home in the evening, then the connection pool will tend to monitor the number of connections. If it notices that some connections have been idle for a long time, then and the number of connections is still above the minimum that was configured, then it will remove some connections. So essentially, this is working by trying to right-size the connection pool to the prevailing workload. And in normal operation, these feedback loops that are built into the connection pool are pretty harmless. They work well for most of the systems most of the time. So you could ask me, well, if my server has lots and lots of memory and lots of CPU power, what's the problem? Why wouldn't I just let that system take over? Why wouldn't I just set a minimum and a high maximum and just let the connection pool figure it all out? Well, in normal operation, there isn't much wrong with doing that. When everything is going well, just having the number of connections floating actually serves lots of customers quite well. But for the purposes of this presentation, where it really hurts is when a glitch occurs, because having the number of connections being very volatile means that a short-term glitch could lead to problems that last much longer than they need to, and ultimately, in some cases, even lead to an outage. So we should cover what is this idea of a glitch. Well, a glitch is almost anything that can interrupt the normal flow of processing in the database. And there are lots of examples that we could consider both within and outside the database. So some that might be happening within the database is if a log write suddenly takes a very long time to complete, perhaps because the storage area network is undergoing a reconfiguration, which can happen when cables are reconfigured. If the log writer gets delayed, then no transactions will be committed and it will be as if the database has stopped. The same can happen in a data guard configuration. If there is a glitch on the network, then that can stop transaction processing in the database. Similarly, things that the DBA or the application developer can do, like recompiling packages or invalidating SQL statements by performing DDL, can result in an interruption in the normal flow. And reconfiguration of the system, for example, if one of the instances in a rack cluster goes away, we can get a glitch where no transactions are processed for a very short period of time. So these things sound bad, and a lot of people would ask, well, how do we go about eliminating them? And there are a lot of things that people already do to build high quality systems and high quality processes and procedures that try to minimize the incidence of glitches. But even the best systems that we see will suffer from the unexpected from time to time. Basically, that's the real world. It just happens. And often these glitches will go unnoticed until something bad happens typically at a peak time in either a business cycle or in the working day. And those are the ones that catch the attention, cause the phones to ring, give us a bad day. And quite a bit of the work that our team does is involved in these sort of escalations. So if we're looking at what will happen during one of these operations, what really goes on and what's wrong with the way that the connection pool that we described earlier, what's wrong with the way that that works when we have a high throughput system? Well, once the database work is delayed, doesn't stop new work arriving. So especially with internet facing systems, you don't ever reach really the situation where everybody is waiting, just more work continues to arrive because the user base that's out there can be very substantial. So essentially, we're not processing the work, but more work is continuing to arrive. So all the connections that we have in our connection pool quickly become active, but not really making any progress. So the connection pool will respond naturally by adding more and more and more connections. So the number of connections will rise very rapidly. And in fact, we have seen cases where the number of connections will rise by thousands in just a few seconds, which of course is way faster than the DBA will be able to react to that situation. And what happens when we have thousands of connections? Well, we actually have some videos that will be available to you after this presentation that walk through this in quite fine detail, building up the situations. But here we get from the situation where all is well, where on the left of the screen we see very low response times and we see very low number of active sessions in the database, and then suddenly something happens and the number of active sessions goes sky high, the wait times increase, CPU gets, in this case, busier, but we're actually doing less work and it's becoming more, the behavior of the system is much more erratic. And you see that the system doesn't recover from that right away. It takes quite a long time for the system to recover. So essentially, we have some very strong guidelines that we have used with a wide range of customers to try to avoid that situation arising in important, fast-moving OLTP systems. And the guidelines are pretty simple. One is that we would want to eliminate the dynamic expand and contract behavior that is built into the connection pool. That's really because establishing a new connection in the database is an expensive thing to do. It's expensive under normal circumstances, but it's really expensive when the system is busy, and it can be compounding the problem. It basically becomes a positive feedback loop. The connection pool adds another connection. The extra connection actually slows the system down, so the connection pool responds by adding more, and we get a positive feedback loop. So removing the dynamic behavior of connection pools is actually a great way of stabilizing the performance, especially for high-end systems. Now, I mentioned earlier that this idea of right-sizing and the connection pool trying to be just right seems very nice and works very well for most of the people most of the time. But the guideline for OLTP workloads at the high end is that you should aim for about right and stick to it. And that really means trying to get the number of processors that are connected to the database to be a natural function of the power of the system itself. So we take the number of CPUs within the system and apply a simple multiplier. And if you think that just one process in principle can be enough to make a CPU fully utilized, we use a simple multiplier that says, well, if one's enough, then 10 is plenty. And the rule of thumb of 10 processors per CPU is a good target to aim for. It's more than enough to make the server busy to get the maximum throughput when we need it without introducing unnecessary waits. But it's not so many that when the processors go busy, that performance overall and throughput especially suffers too much. So it's a great compromise that has served us well. So that is essentially one of the strongest things that we recommend for OLTP systems, and most of the time that rule of thumb can be applied. It often meets with a lot of resistance to be able to implement it successfully, but it has been very successful in converting unreliable, unpredictable systems to smooth running, reliable systems, which is exactly what we all want after all. So though I can't really recommend these sort of strategies highly enough. It's been very valuable in the work that we have done over the years. However, very little stays the same in the world of computing, and the application development model continues to evolve, and the more modern application deployment techniques tend to result in systems that are scaled using multiple containers, for example, using technologies like Docker to be able to quickly expand and contract the number of applications in application servers in response to the workload. So rather than, as might have been done way back, reconfiguring machines or buying additional machines, we just roll out more or start more containers, deploy more containers, and away we go. And that technique tends to result in a very high multiplier. We have seen systems with hundreds and in some cases thousands of containers, each of which will have its connection pool. And that connection pool is going to need a certain number of connections to the database to get its work done. So sometimes it's really hard to meet the guidelines because the multipliers become so high. And this is where we have a new technology called the proxy resident connection pool. And for the rest of this presentation, what we're going to look at is how the proxy resident connection pool differs from the deployment models that you'll have previously seen with Oracle. And this is very much a technology aimed at the cases where we have lots and lots of application servers connecting to the database so that we can't easily apply our previous guidance. To get to the PRCP part, the slide gets more complicated, so I'm going to start with something really simple, which is how it used to be in the olden days, where in the client-server world, we would have multiple versions of the SQL+ diagram that I showed you earlier. So we have clients connected to the database, and once they're connected, they stay connected. And with the old client-server model, each user had its own process and stayed connected for the whole of the working day, potentially. And that session would hold a process on the database and hold memory and so on. So it's not very scalable when it comes to very large numbers of users. And it's just not very practical at all when it comes to internet-facing systems. So in the early days of the internet, systems would typically connect to the database, do their work, disconnect. That was there for CGI bin type processes, and it was also there for PHP and others. So there was a lot of development done by the application in the application tier and at the database side to come up with strategies that made that connect-disconnect model less expensive. And one of those from Oracle is a technique called DRCP. And this is the Database Resident Connection Broker. What that essentially does is it says that instead of on connection starting up one of these heavy, expensive processes to Oracle, well, we already have them started. So the broker will find an available process that's already authenticated with the database, and my application session will use that for a short period of time and then return it. So all of the brokering work is being done on the database, and that takes away the high cost associated with repeated connect and disconnect. Doesn't make it zero, but it reduces it by a substantial amount. And this technique basically allows for single-threaded applications in the application tier. So we had DLCP introduced a few years ago, but most modern applications tend to be built around a model that says, well, rather than having the database do the sharing of connections, why wouldn't we do that in the application? And this is the connection pool that we described just a little bit earlier, where there is a pool of connections established to the database. The application will borrow from it, do the work, and return it. Now, this does require that my application be written in a way that fits the pattern. I've got to be able to acquire a connection, do work with it, and then return it. And of course, modern applications tend to be written in this pattern, but we can't simply retrofit it to the oldest of applications. So it is a specific development model, and it requires a multi-threaded client for this to work. So essentially, the core of session pooling is that it's not there for all applications, but for for the majority of applications that have been developed in the last decade to 2 decades and possibly more, then connection pooling has been a core part of the technology stack, whether it be done as a technique in the database using DLCP, or more often within the application using an application-side connection pool. So some people will have heard of this technology from Oracle called the shared server, which is yet another method of connecting to the Oracle database, and might wonder, well, does the shared server have a place within this model? The shared server was originally designed back in the client-server era to support very large numbers of long-lived clients. So it doesn't actually require any specific programming model, but it also has the disadvantage that this dispatcher process is doing quite a lot of work. For every SQLnet round trip, the dispatcher has to retrieve the message, put it onto a queue where the shared servers pick it up. So there's a lot of extra code path in the shared server. So we only see this, or we seldom see it these days, apart from as a band-aid where the number of clients go up. So we have various different models, some of which are impose quite a lot of discipline on the application. It has to fit a certain pattern. Others which will work for everything, and those have different scalability profiles. So let me just move this. So for the dedicated, the shared server model will support any style of application, but it potentially requires more resources on the database tier, because the connection management is being handled by the database server itself. So having given you the build-up with all of the different models that have been out there for, in some cases, years and years, and DLCP for a decade or so, the proxy resident connection pool is a newer technology from Oracle. And what this is designed to do is to say, well, I don't like burning my database CPU time just managing connections. Why wouldn't I try to find a way to do that on a server that is outside the database, so that I get the maximum performance from the database, and maybe use additional systems, perhaps lower cost systems, to do this connection management. And that's what PLCP is all about. It's about moving the cost from the database tier and into a separate set of servers that simply manage the connections between the clients and the databases. And it's particularly good for the scenario where we have lots and lots and lots of application servers, because it sits in a model where we are able to use not just one funnel, as we have in this particular slide, but we can actually run with what we would call double multiplexing. Some people would say double funneling of connections to the database. So we can take our multi-threaded client application, which has its own connection pool, and then use the proxy resident connection pool to manage that large number of connections down onto a smallest possible number of database sessions at the back end. So essentially, we're taking the strategy that fewer connections is better, more efficient, faster, more reliable, and we're using these PRCP in the middle tier to help us achieve that, even when there are many, many application servers outside the database. The price of this is actually that you're going to get an extra network hop between the application client and the database, because the message has to flow through the PRCP machines and through onwards to the database server. And typically that might add about a millisecond or so to the response time for a fast executing SQL. Now, a human being might not notice that, in fact, almost certainly won't, but a batch process might. So this is very much aimed at online transaction processing, where we have lots and lots of users at the left-hand edge driving the workload. So all of these pooled models actually require the same kind of application programming model of being able to acquire a session from a connection pool, do work with it, and then return it. But we can see that all of them have reasonable levels of scalability, but the ones with the highest levels of scalability tend to be the connection pool applications, so the modern technique, or connection pools on top of the PRCP, which is able to go to even larger numbers of application servers. We do have some outline results from testing with the different technologies on one of our in-house systems. So essentially this workload is an OLTP workload where we scale up the number of, we scale up the workload, essentially scale up the demand, and we monitor how much work gets done, how many transactions per second, and we monitor how busy the database will be when it's handling that workload. And we also monitor the database time, so how much time is actually spent within the database processing the SQL statements. And what we can see is quite a nice linear relationship between the amount of work and the CPU consumption. The green line is the CPU consumption. But we see that as the system starts to get busier, the CPU consumed within the DRCP component means that the system is consuming a larger and larger share of its available CPU resources, and the DB time is non-linear beyond a certain point. It's never catastrophic. DRCP is pretty well behaved for this workload, but we can see that it deviates from the straight line, the lovely straight line behavior beyond a certain level, just because we're getting the overall system busy, and the DRCP processors are having to compete with the foreground processors that are doing the useful work. So let's take a look at PRCP with the same workload scenario. What we see is a couple of things. Actually, the green line does drop a little. So for the same throughput, we are using appreciably less CPU time on the database server. So this idea of using PRCP to move the connection management outside the database has worked. It has reduced the CPU load for a given level of application throughput. And in return, we now get a much smoother line for the database time. So the database time only begins to deviate from the straight line as the system really starts to get very busy. And because we have so few processes running within the database, there's very little wait. So for a DBA's perspective, the wait events are kept to an absolute minimum. The main one in this workload, because it's transactional, is the log file sync that we would expect to see in any OLTP application. So I've actually got through this a little bit quicker than I expected to do, but one of the things that I wanted to do, because I know this topic tends to raise quite a few questions, is I wanted to summarize what we have been describing, because I think that there are two situations here. One is for most of the people, most of the time, and then we have for customers with very large systems with high throughput, an extra technique that could be of interest. So for most workloads, the recommendations that teams like Real World Performance have been making for many years now of limiting the number of connections to the database, those recommendations have served as well and continue to serve as well for the vast majority of systems out there. Our finding has been that 10 processors per CPU is almost always more than enough. And in fact, there are systems out there that run very well with fewer connections per CPU, because especially in the modern systems, the processors aren't spending a lot of time doing I/O and so on. So we don't have to have too many processors just to get the CPUs busy. So thinking about the number of connections to the database is a very important element of giving systems the smoothest possible experience, so that we get the best behavior from the system. And of course, when the systems are running smoothly, we don't get calls asking us to fix problems and so on. So it makes the overall behavior of the system much easier for customers to manage. And we do see systems that go from being endlessly troublesome to being very smooth running simply by adopting these very simple policies. However, if we are at the high end with lots and lots of application servers out there, because we're using a deployment model that is maybe microservice based or simply is scaling horizontally using lots of relatively small application components, then the PLCP technology has so far in our testing showed to be very promising in the way that it helps us manage down the number of connections to the database. So it's giving us that ability to manage down the number of connections, even when naturally we would need a whole lot just to support the number of application servers and connection pools that are out there. However, we already mentioned there's no such thing as a free lunch for PLCP. It introduces this extra network hop, which does increase the latency for very short-running SQL statements. So typically, we see the extra network hop will cost about 1 millisecond, and Oracle's able to process SQL statements in under a millisecond. So for some workloads, that extra time might be significant. However, we should remember that Oracle's a pretty versatile product, so we can mix and match the technologies. So PLCP can be used for what it's good at, and we can fall back to straight through dedicated sessions to handle, for example, queue processors that need to have a very low latency of response time to pump messages from one component of an application to another. So we have got methods that we can use. Because PLCP is a relatively newer technology, we don't have lots and lots of reference sites that we can point you to say, oh, well, it's worked well for this customer and for that customer. So for that reason, our team is particularly interested in customers who would be interested in investigating PRCP. So one of the things that I know Jürgen mentioned that we should do is, as part of the Q&A for this session, we'd like to take any take contact details for anybody who's got an interest in this proxy resident connection pool for managing applications that do naturally create very large numbers of sessions in the database. So I see that there are quite a few Q&A and chat questions coming through, and I think I have just a few minutes to answer questions. So I wonder if now would be a good time for one of our team to see if there are any questions that they would like to answer live.
Well, let me read it, this, Mike. So there's the question, do we have a white paper on this for OLTP workloads? I think you want to answer that.
We do have some documentation for PRCP, but as part of one of the feedback cycles that our team does, one of the things that we have been feeding back to the development team is that we do need easier to follow guidelines for customers when it comes to choosing the parameters that go with the PRCP. So we do have some sessions that were done at Open World in 2019 from the team that actually developed this software component, and that is one that I could recommend. It does have a little bit more of the details of when you would configure it in particular modes for certain applications and drivers, and that's got a little bit more detail than I've been able to cover here today. So one of the things we could do is circulate that as part of the perhaps circulate that as part of the presentation that when we share it. I do see another question in there, which is, does PRCP require an extra cost license? The answer is that although I'm not a licensed person, no, it does not. In fact, it is one of those technologies that is essentially can be deployed on servers that are not specifically licensed, because its only function is to deliver connections through to the Oracle database. So one of the virtues of it, if you like, is that that it is offloading the CPUs from the database server and moving that connection management work into another place, which doesn't require a specific extra cost license, or indeed actually any licensing at all. We have a question saying, which versions of Oracle database does PRCP support? PRCP is restricted to 18C and 19C.
Okay. Anybody? Any other questions from the forum here? Okay, Mike, you see the question here?
Yeah,
Ravi?
I see the question from Ravi. How can we drive customers to use PRCP instead of traditional JDBC connection pools? Well, I would say that the traditional JDBC connection pool is not at the end of the road. It works well, as I was saying, for most of the customers, most of the time. So the specific use case that fits best for PRCP is when we do have many application servers. That's typically going to be measured in many tens, maybe hundreds or thousands. So that's the thing that would tell me that it's a time to think about using PRCP. I mean, we do have questions that come through on internal mailing lists every now and then that say, how am I going to get Oracle to support 30,000 connections and so on? And those ones tend to be the case where the number of application servers has become a very large multiplier. So that's what I would look out for.
Well, let me supplement this. Even if you have today an existing application server farm where you have dynamic JDBC connection pools, even those you could connect through a PRCP server. PRCP to those is basically transparent, and you can basically switch gears from there. Then there was another question about how do you see in an AWR report that you have a problem with these connections. Number one, it's the total number of connections you have in the first place. And then if you see dynamic connection pooling kicking in, is if the system is getting under stress or certain workload processes are kicking in and you see a rapid increase on connections into your system. Mike mentioned the rule of thumb about the connections per physical core. So I think that is a guideline you should look at. If you are in the thousands of connections to a system, that's very questionable, and you're exposed to risk that you potentially drown your system.